So in these very tutorials, we shall be looking at what we call symmetric functions. Remember, we are still on the same topic, quadratic functions. If you have not subscribed to the channel, kindly click on the subscribe button to get notification whenever a new video is posted on this very channel. When we talk about symmetric functions, what does it mean? So let's take it that, or given that alpha and beta are the roots of a quadratic equation. So this is alpha and this is beta. Let's take it that these two are the roots of a quadratic equation. And you have a function which is in terms of this alpha and beta. Now when this function, which is in terms of alpha and beta, remains the same whenever we interchange alpha and beta, then you can say that that function is a symmetric function. An example of a symmetric function is this, where you have alpha squared plus what? Beta squared. Now when we interchange alpha and beta, meaning when you bring beta and then we have alpha squared, this function remains the same. In that case, this function is called a symmetric function. Another example of a symmetric function is 1 over alpha, then we have 1 over beta. This function will still remain the same whenever we interchange alpha and then beta. In that case, then this function becomes what? A symmetric function. The basic symmetric functions or the elementary symmetric functions are alpha plus beta and then alpha beta. These are the basic symmetric functions because when we interchange alpha and then beta, this function will still remain the same. The value will still remain the same. When we interchange alpha and beta, the value of this function is still going to be the same. In that case, these functions all becomes what? Symmetric functions. So when you know these two basic symmetric functions, which is alpha plus beta and then alpha beta, we can use this to calculate any symmetric functions of our choice because there are countless examples of symmetric functions. I believe you are following me. In our previous lesson, we were able to establish that if alpha and beta are the roots of a quadratic equation, then the sum of these roots, which is in terms of alpha and beta, is the same as minus b all over a. And then the product of the root, which is in terms of alpha and beta, is the same as what? C all over a, where a and b are the coefficients of s squared and then x respectively, and then c is the constant of the quadratic equation. So you are going to base on this concept to find the values of these symmetric functions. So let's look at the example. It says that if alpha and beta are the roots of this quadratic equation, we should find the values of this symmetric function, this symmetric function, this, and then that. So what we are going to do is to identify our A, our B, and C from the quadratic equation. So from the quadratic equation, our A is the coefficient of s squared, which is 2. Our B is the coefficient of x, which is minus 1. And then RC is the constant, which is minus 2. So once we are done with this, we find the sum of the roots. And we know that the sum of the roots is giving us alpha plus beta. And this is the same as minus b all over what? A. So from this, RB is minus 1. So we have minus 1 all over what? A, which is what? 2. And this is going to give us 1 all over 2. And then we find the product of the roots, which is giving us alpha multiplying what? Beta, which is the same as C all over what? A. RC is minus what, 2? And RA is what, 2? So we are going to get minus 1. So once we have this, let's look at the first symmetric function. So once we are done with this, the next thing that we are going to do is to massage this symmetric function such that at the end, we are going to have alpha plus beta and then alpha beta within, so that we can do our direct substitution. Since we are having fraction, we can find what, the LCM. So the LCM of alpha and beta will give us alpha, beta. Alpha into alpha, beta, we have beta. Beta times 1 will give us what, beta. And then beta into alpha, beta, we have alpha. Alpha times 1 will give us alpha. Since addition is commutative, we can rewrite this as alpha plus beta all over what, alpha, beta. So you can see that we have alpha plus beta, we have alpha plus beta, which is this, and then we have alpha beta, which is that. So we are just going to plug in these values. So alpha plus beta, we had 1 over 2 divided by minus 1, and this is going to give us alpha 1 over alpha plus 1 all over beta is going to give us what, minus half. As easy as that. Let's look at this particular one before we come to the second one. Now remember that alpha squared plus beta squared is not equal to alpha plus beta or squared. Take note of that. Now you want to find the value of this symmetric function. So what we have to do is to massage this function such that at the end we can have alpha plus beta and then alpha beta. So looking at this, you realize that when we expand alpha plus beta all squared, we are going to get something of this form inside. So let's expand it. This is going to give us alpha squared plus alpha beta plus beta alpha plus what, beta all squared. Let's do some rearrangement. We have alpha squared plus beta squared. This and that will give us 2 alpha beta. And this is equal to alpha plus beta all squared. Now our interest is to find alpha squared plus what, beta squared. So we have to transpose 2 alpha beta to the left hand side. So we are going to get alpha plus beta all squared minus 2 alpha beta is equal to what, alpha squared plus beta squared. So we have gotten what we wanted, which is this one. So we can say that alpha squared plus beta squared is giving us that. Now once we have this, what we are going to do is direct substitution, because we have alpha plus beta, alpha beta. So we just have to plug in these values in place of what, this. So we have alpha, let me rewrite it, well, alpha squared plus beta squared is equal to alpha plus beta will give us 1 over 2, or we have 1 over 2, but this is what, squared. And then 2 alpha beta, we have minus 1. So when you do the algebra, we are going to get 1 over 4 plus what, 2, and that is going to give us what, 9 all over 4. So this is the value of this symmetric function given this quadratic equation. Let's look at this particular symmetric function. So we have this symmetric function. What we have to do is to massage this symmetric function so that we can have alpha plus beta and then alpha beta within. So in the course of doing that, we have to find our what, LCM. So the LCM of alpha squared and then beta squared will give us alpha squared multiplying beta squared, and which is the same as alpha beta or squared. So alpha squared into this, we are going to get beta all squared, beta squared into this, we are going to get alpha squared. So with this, we can rewrite it as alpha squared plus what? Beta all squared, since addition is commutative. And then all over alpha, beta all squared. But with our previous example that we did on this, we said that alpha squared plus beta squared is given as what? Alpha plus beta all squared minus 2 alpha beta. So it means that in place of this, which is this, we are going to substitute the whole of this in place of what? Alpha squared plus what? Beta squared. So you can see that 1 over alpha squared plus 1 over beta squared is equal to alpha plus beta all squared minus 2 alpha beta all over what? Alpha beta all squared. So we will have alpha plus beta, we had 1 all over 2 squared minus 2 alpha beta, we have minus 1 all over minus 1 all squared. This will give us 1 all over 4 plus what? 2 all over 1. And when you simplify, you are going to get what? 9 over 4, as easy as that. Let's look at the last symmetric function, which is even. So let's look at this symmetric function. So looking at this, you agree with me that when we expand this, we are going to get alpha squared minus alpha beta minus beta alpha plus what? Beta squared. Our intention is to have alpha plus beta and then alpha beta so that we can plug in this value. That is the reason why we expanded this symmetric function. Now when we do some grouping, we are going to get alpha squared plus beta squared. This and that will give us what? 2 alpha beta. And we have already established that alpha squared plus beta squared is giving us alpha plus beta all squared minus 2 alpha beta. So this means that in place of this, we are going to substitute the whole of that, or in place of this, we can write this. And then we have this minus 2 alpha beta. So let's do some small simplification. This and that is going to give us 4 alpha beta. So at the end, you agree with me that we are having alpha plus beta and then alpha beta, and therefore we can plug in our values. Alpha plus beta, we have 1 over 2 squared minus 4. Alpha beta, we have minus 1. This is giving us 1 over 4. We have plus what? 4. And when you simplify, you are going to get what? 17 over 4. This brings us to the end of today's lesson. See you tomorrow. Bye-bye.